So hello everyone, welcome to the last tutorial of the last week of Macbeth Hacks. We have our mentors Vamsi and Nii, and they will be talking about, they'll give a tutorial on model generalizability. So without further ado, I invite Vamsi and Nii to introduce themselves, talk about their career interests, and then they get started on the tutorial. The tutorial is already, like the material for this tutorial is already uploaded on Gumroad, so I'm going to share my screen real quick, show you guys where it is. So in Gumroad, under week 8, we have the Google Drive that we click on, and inside the workshop folder you have the workshop material that was given last Saturday, and then we also have the assignment. So there's 2 notebooks. One of them is from Vamsi, the other one is from Nii, and they will get started going over these notebooks for you guys. I'm going to share this and put it in the chat as well. So without further ado, yeah, you guys take it over. Thank you so much.
So Nii, you wanna go first, or shall I go?
Yeah, you can go first.
Oh yeah, sure, no worries. Okay, yeah, so I'll just share my screen. Okay. Hussein, could you
Yeah, just it.
yeah. Oh yeah, I think he gave it to me. Yeah, no worries. Yeah. So okay, yeah. Okay. Oh yeah, I hope like my screen is visible to you guys.
Yes, it is.
Okay, so like so this so I'll first introduce myself. Like yeah, so my name is Vamsi Krishna, and like presently like I work in the NLP and speech domain at Huawei Montreal lab. So I'm a researcher there, and like we mainly work on information retrieval and making web search engines using LLMs, large language models. And also we do some task-based cross-task transfer analysis on speech recognition models like Whisper, like recently, which OpenAI introduced. So these are my interests usually. Like these are the topics we work on. And so now I'll like explain like the tutorial, like the assignment. So this particular assignment was mainly like mainly focused on how like we can, if we have an imbalanced data set, how can we upsample the minority class and like improve our recall score. So we are taking recall score here mainly because assume there's a case like where there's fraud detection or something like that, credit card fraud detection happening. And we might have very less samples which are classified as fraud, whereas a lot of samples would be there which are not, which are classified as non-fraud. So at this point, we want our model to have a high recall so that we don't miss out on any fraud cases. No fraud cases are misclassified as non-fraud, but it's fine if we still classify a non-fraud as a fraud one. The reverse is still fine. So we look for a high recall, and that's what we are trying to do here. So I'll go ahead. Like these are the libraries we have used it. It's mainly uses sklearn, and like we use pandas and numpy here, like based on the usage, like however people prefer it, like to handle the vectors. Also matplotlib for plotting, and seaborn like makes it more beautiful to like present it, like makes it more pretty, the plots. And IMBlearn is another library which is specifically dedicated to imbalanced classification. So you can check this out, and they have like various oversampling, undersampling techniques like already implemented. So it's very easy to like use it like from the shelf, and like you can try out different things and see whether it works or not. So this particular tutorial is focused on SMOT, like this is the technique which we'll be seeing today. So I'll just go over like the tutorial. So when you see like the data set, I have taken it, like we have taken it only, we have made it using random data points. just to understand like how imbalanced data work and how can we improve it. So there's no specific data set taken, but this technique applies to any data sets as well. So we do it like by using the make classification method. Like we can mention the number of samples and features, number of features we want, and number of classes, how many clusters, and weights are mainly telling like how much weight do you want to give to a major class and a minor class. And based on this, like we take 10,000 samples. So you can see it has created a data set with minority samples are about 9897 and majority are 9897 and minority are 103. And then the question one was to split the data set using train test split. So we do that using the train test split command, which is available in sklearn. We need to just provide the main data set X and Y, like the labels and the features and how much do we want the test size to be. And random state could be set to like anything like this. So usually it tries to randomize it. You can fix it like while you're experimenting so that the test and train remain the same always. And we can see it has split into 80 and 20%, like how we asked it to. 8,000 samples go to training, 22,000 go to test. This case, you can also like switch on the stratify like argument as well. That also helps. And that helps so that the distribution is kept equal both sides. But here it's in a way like it's fine, like in this case. And then the second question was to take a scatter plot. So I would like always I have also learned over the time to take this practice like whenever you're starting off like plot the data set, or else try to understand the distribution, like how is it distributed over the range. And this helps us in understanding like which algorithm should we go ahead with, or do we need to make any changes to the data set as such? Do we need to normalize it or standardize it? Those kind of techniques could be like understood. So it's always better to have a plot. So in this case, we just have two of these. So I do okay, I think I can make it small. Yeah, okay. So this is the scatter plot. Like if you see, so target like a 0 is the majority class, and we can see a lot of the points are there. A lot of points are there, and 1 like is spread out, like because it's a minority class and it's being spread out. And so based on this plot, we just understand in this case it's like ones are less and zeros are like at a point, like they are clustered at a point. So next, like as we say, like before building the model, we always need to decide like how are we going to evaluate it. Like we need a metric to evaluate like that case, and we always need, like in this case we can't take accuracy, because I think as we learned during the theoretical class as well, like accuracy might like mislead us, saying like a model is working very well even though it only classifies the even though it only classifies the majority samples. Like even if it gives like 0 completely, like we get a 99% accuracy, but the model is not able to detect like the fraud, like minority class, so which is important for us to detect. So hence we go with the recall as our evaluation metric here, because that will help us like to understand like whether the minority classes are being classified properly or not, like and is the model being able to do that like as well as we need it. And so here I go with the algorithm which we use for this particular experiment is random forest. So there's no such like random forest is usually like there's no such reason for this data set, like why we have taken it. But usually it is good like when you want, it usually works well on imbalanced data to some extent, because random forest is nothing but an ensemble of decision trees. So the way this algorithm works in short is like a lot of decision trees. So maybe I can show what you here. Yeah, so yeah, something like this. So a lot of decision trees on the same data set are being applied. Like this data set is being like sample out random amount of samples from the same data set and construct different decision trees, like n number of decision trees, and then each decision tree gives out a prediction. And then we take a hard voting system or soft, like we can do it both ways. Okay, sorry. Yeah, we take a hard voting system where we try to understand like which particular class label is getting the higher weight, and based on that we decide like okay, we will be assigning this label. So this helps in reducing the variance in a way, like the variance is reduced, and so the model is more generalizable, and like the solution is more trustable, like, and can be explained well. So we use a random forest classifier, so it's pretty much easy to use it. Like with sklearn, you just need to instantiate it from the random forest classifier class and then fit it to the X train and Y train, the usual one which we do, and then like make a prediction on X test, like the test test data set which we have, and then we use the recall score, like recall score methodology here, and using the Y test and the baseline prediction we have, Y true and Y pred, and we see like it gives about 29.41 as of now, like with this, I feel this is still working to a good extent. Like we haven't done anything, and the imbalance is very huge. Still, it's able to do something. Like it's able to predict the negative samples to a good amount of extent. Like it's able to 29% of it negative samples are being predicted well. And but this is very minor, so we would like to for sure improve it ahead. So what we do is this the oversampling technique, which is synthetic minority oversampling technique. So how it works is like I can show it here. So after applying it, like yeah, maybe I can explain the working once through this graph. Okay, so I'll explain first the usage. So you can use it pretty easily, like using sklearn's SMOT function, and you can instantiate the object from here, and then like you can provide the X train and Y train which you have as of now, and you can use fit resample and get a resampled version like of equal sizes, like you can say 50% test and 50% majority samples and 50% minority samples. And now if I show the graph, like you can understand here, like if you observe, there were few points here, like the points were scattered. So how it does is like it tries to find a cluster point in between, like using k-means. So the k-means is the algorithm which it uses, and it tries to find a center point, like between these minority samples, each of these minority samples, and then like along these lines, like which is a centroid point for a k-means. Along these lines here, you can see this is one line, this is one line, this is one line formed. Like if you see, there's a pattern formed here. So it tries to oversample and plot the points like this. And we make an assumption like these points are of the similar distribution as the ones we have here. So in a way, we aren't harming the model much, like, but at the same time, we also get the advantage of having more samples which are of the same distribution. So k-means helps us in identifying the distribution of the minority samples. And once we know the approximate distribution, we try to oversample and place the samples according to it, so that the distribution is maintained. Because as we have learned before, like the distribution should be same on both sides, like train and test, to make it same, like so that the results are good. So once we do it, I think we have good enough points on both sides, like and now we can go ahead with the classification again. So now we don't do anything like anything separately, like new or something. We just do the same thing which we did above. We use a random forest classifier. We fit it to X train and Y train SMOT, but this time it's the new oversampled version. And then if you predict it, like the recall score has gone up, like now it's able to detect like 50% of negative samples, like when I say 50% of minority samples. And this is a good amount when compared to before. We almost like some extent like doubled it. So this usually helps. SMOT helps in increasing the recall score. And if you have a condition where you want the recall to be high, this can be used for sure. So there are other techniques as well: random oversampling, random undersampling, near miss undersampling. Like there are few more techniques which can be applied, like these. I think you can try it out, like, and see. I guess I have tried one of them, which is random oversampling. And a random oversampling is nothing but we randomly, like, just throw the points into the space, and new points into this 3D space, and try making the model predict them. But this hasn't offered me a lot of improvement as far as I tried. But based on my past experience, the other two might help. Like undersampling is something like it should be applied usually after oversampling. So how the pipeline works is, for undersampling is like, you have X data set which is imbalanced, you apply oversampling, make it oversampled. Then if you feel you want to get it down, then might be undersample it like a little bit. So direct undersampling usually doesn't work that well, but you can do it like start oversample and undersample that. So yeah, these are few techniques. And yeah, I feel this is it, like, for the tutorial. And I think, like, I just wanted to explain, like, how, like, these techniques help us in improving the score when there's an imbalanced data set. And still, like, rather than gathering more data, we can still data is anyways always good. Like, if we have more minority samples, it's always good, because data is the best regularizer you can have. But still, like, these work when we can't get data, like these two. So yeah, like, that's it from my side. Yeah, please let me know if you guys have any questions. Yeah.
different ways that the
Great.
tool can talk by
Thank you
itself.
so much.
So you
Oh yeah, Jose.
all these
I'm just like saying thank you so much. That was nice.
Oh yeah.
all these
Oh yeah.
modalities,
And
that you
yeah, I guess like it's now Nee can explain.
Yeah,
her
sure,
stuff.
sure. Yeah, sure.
Thank you, Vamsi, for the tutorial. It's very useful. Yeah. Okay, I will start my screen now. Can you all hear me well?
Where
Yeah,
Oh,
and
yeah.
we can see as well.
similar
And can you see my screen?
Yep.
Oh yeah, we can.
Okay. Yes. So it's my pleasure to like mentoring for the final week of Mathematics. So for this week, I will talk about like model generalization and some common practice for it. First, I will show you some common practice to ensure model generalization, in which there are two types of main techniques, which is data-centric and model-centric. For data-centric techniques, you want to understand the data distribution and understand the evaluation matrix. Then you can apply some data augmentation and determine a good cross-validation strategy for your models. For the model-centric techniques, it's more like you focus on the model itself by reducing the capacity, try some early stopping, weight decays, and samples with some regularization. But like for simplicity, I will focus on the data-centric techniques, which Dr. Leia talked about like during the workshop. So I want to have like a quick recap like on her workshop. So she mentioned about she mentioned about cross-validation, which I talked briefly about on week 2 assignments. You can refer to this at some like reference point. Then she also mentioned about the specific metrics, which I'm gonna talk about in this assignment. And finally, she talked about, she talked about data augmentation, which I also have some tasks for you for this assignment. Okay, so I will go over the assignment. So this assignment is built on the week 2 assignments. So I will go over it quickly, which I prepare a subset of data set from the RSNA screening mammography breast cancer detection competition on Kaggle. However, this data set is a bit bigger than the data set I prepared for week 2. So you just need to clone the GitHub repo here, and then it will need to run this first. You're gonna clone the GitHub repo, and then it will have all of the DICOM data for this assignment. Then you just need to load the train data frame and do some analysis on it. For the meta-analysis, I would just, for simplicity, I just want to focus on whether the patient has cancer or not. So I will plot the distribution of targets where the non-cancerous image gonna be represented as 0, and non-cancerous and cancerous image gonna be represented as 1. So as you can see, this data set is highly imbalanced. And because it is imbalanced, we need to pay more attention to the minority class. And in this case is the cancer class. Okay, then we go to, let me see if it's still cloning. Okay. Then I will go briefly to the DICOM image analysis, and just to read the DICOM file, and then have some simple preprocess on the DICOM file, in which I will just load it and then access the pixel data, then normalize it using min-max normalization, and then choose the monochrome, which this stand for like the ray scale. It would be similar to the ray scale image. Then I will also resize it to 512 by 512 for like to make the visualization like easier. Okay. Then I also define some helper function to visualize a batch of images. Then I define a breast cancer data set, which is like kind of a foundation later on if you want to train deep learning models on it. Then I will just like call the RSNA data set and then load it to the data loader with the batch size of 16. Then I will visualize a sample batch of 16 images. Which gonna be something like that. Just a second. Okay, now I will talk about data augmentation. So like earlier, Vamsi talked about oversampling, undersampling techniques, which is very useful for like machine learning and deep learning. However, for unstructured data such as images and text input, upsampling or downsampling will sometimes not so effective, especially in the case of computer vision. Because like each image is kind of like a tensor representation of pixel. So oversampling or undersampling will like altering the pixel values, which is not like recommended, and it can change the meaning of the pixel of the picture itself. So that's why we're gonna have data augmentation to kind of replace oversampling or undersampling for images, in which like an image gonna go into a lot of transformation, but it still try to keep the meaning like useful. So that there are some common image augmentation techniques, such as flipping like horizontally or vertically, scaling with like different scaling size, jittering, in which you're gonna inject noise to the image. Normally it's gonna be some random noise or Gaussian noise. And then you can have like rotation, which like with different angles. And then cut mix is similar to coarse dropout, in which like they're gonna try in which it's gonna try to randomly cut a certain part of the image. This one is kind of like an advanced technique because it will make an image harder for the model to learn. But like once the model can learn that information, it will be like very useful and it can generalize very well in the test set. Below, I also give some resources for the handling imbalanced data and augmentation, which is the library that I'm using for mostly all image augmentation pipeline. You can go over this library, and they also have a lot of example and tutorial pipeline. They even have a demo. You can look at, oh, it's right here. They have a demo in which you can try like different things to see how the image transform and which one makes sense to your problems. Okay, so for simplicity, I will just go over some flipping, rotation, and cut mix. So this one is the horizontal flip, and then I rotate it, and then a coarse dropout. You can see the black rectangular box here. This one is gonna be like label as 0 as a background, and then the model gonna try to learn what information contained in this black rectangle box. So task 1 for you is to create a data augmentation pipeline of your choice. So you can go over the augmentation library and go over of no, not this. Go over of the transformation and then try to apply it here. And in this case, I will just use horizontal flip, vertical flip, and then I downscale the image, and I random erase some of the information from the image. You can choose different one and visualize it. After that, you can test it by visualize the batch of augmented data. Just need a few seconds for it to run. Oh. With a particular orientation flip is the flipping and rotation? Yes, that's a very good question. So sometimes you need to make sure that your augmentation pipeline makes sense to the model. You don't want to like distort the information too much, and in that case, like it would be useless for the model to learn. So again, it depends on the task and the use case and the medical images. You can try to rotate like to a certain angles, but not like to rotate it upside down or something like that. Okay. Yeah, for example, this one I rotate it too much. However, the information is kind of like similar to the one like next to it. So in this case, I think the model can still learn a bit from this transform image. And this one is the coarse dropout. Just a note, you don't want to have too many cut mix rectangle like this, because sometimes it will like block the whole like the cancer information from the image. So do it like with cautious. Next, I will go to evaluation metrics for classification. So an evaluation matrix quantify the performance of a predictive model. So for classification, there are three types of metrics that we normally use. First one is the threshold matrix, the second one is the ranking, and the third one is the probability matrix. For the threshold matrix, this one will quantify the classification prediction error. So the common metric we use are accuracy, precision, recall, sensitivity, specificity, which are kind of like F1 score. And there will be some modification of F1 score, something like that with beta, which I will talk about later. For the ranking matrix, it will try to evaluate classifier based on how effective they are at separating class. And in this case, it's like the region under the curve, area under the curve, something like that, or precision, recall, area under the curve. For probability matrix, instead of trying to quantify the prediction error, they will try to quantify the uncertainty of the classifier prediction. In this case, you can just give a probability like, just give the probability and it will calculate the uncertainty. So in this case, you're gonna have like log loss, balance log loss, or weight log loss. For simplicity and for the specific problem we are doing, I will only show the implementation of the threshold matrix, which gonna be like accuracy, precision, recall, and the F1 score, or you can call it die score in segmentation problems. I assume in less than 10. Oh, okay. 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 I assume that you know like TP, TN, FN, and FP stand for, but in case you don't know it yet, TP stand for true positive, TN stand for true negative, FN for negative, and FP for positive. I also put the resource here. You can like it will you can go over it for more detail. For accuracy, you're gonna have the label, which is the round truth, and then the predictions. You're gonna try to calculate the intersection of true positive and true negative, and then like sum up all of the true positive, true negative, or negative, and false positive, and then get the accuracy. In this case, I round it up to 3 decimal numbers. Similarly for precision and recall, in which just like follow the formula here, calculate the true positive of between the label and your prediction, and then divide it by the true positive and false positive. For the F1 score, it's gonna be like 2 times true positive divided by 2 times true positive plus false positive plus false negative, which gonna be like the intersection and then the total sum, and then you divide the 2 times intersection by the total sum. In here, I will I also provide you a helper function, so you can like plot the matrix and compare those metrics on a table. So for example, given the label, this is like the round truth labels, an array, a number array of 1 by something, I'm not sure, 1 by 1, 2, 3, 1 by 9. Okay. And then your prediction is also an array 1 by 9. Then you calculate the label and prediction. You can see the precision and recall is going to be 0.5, 0.5. However, the accuracy is quite high in this case, which is 0.667. The F1 score is slightly higher than precision and recall, but lower than accuracy. So that's why finding a right the right evaluation metric is important. Sometimes you want to put, sometimes you want to make sure that the model don't just learn from the maturity class and then predict everything based on the maturity class. And in this case, it's gonna give a very, can you enable this?
Also a transformer here, whether.
Sorry, what?
Transformers.
Can you enable the screen sharing?
Yes,
Thank you.
They're very sensitive to.
Okay, where is it? Yeah. Okay, thank you. Oh. It's almost at the end of the assignment of the tutorial. Okay, so I guess somewhere around the helper function. So I will repeat this again. So after you calculate the precision recall accuracy F1 score for this label and this prediction, you can see the precision recall and F1 score are kind of similar to each other. However, the accuracy is quite high. And if you want to pay more attention to a minority class, you don't want to use accuracy as your evaluation matrix, because it would only try to learn from the majority class and then have a very high accuracy, but then your model cannot do well in predicting minority class. Okay, so for the task 2, I will show you like the formula, and then your task is to implement test and then compare it with the probabilistic F1 score. So this one is you're gonna have a beta, so you want to like play around with the beta parameters and see how it affects the probabilistic F1 score. For this one, you're gonna have like 2 times the precision and recall divided by the precision plus recall. P stands for the probabilistic, and in this case, it's also a beta parameters. You can try to factor it out and like implement it. There's a lot of way to implement this evaluation matrix, but this is one way to do it. The resources is here. You can click it and see it with more detail. Yeah. First, you're gonna try to calculate the prediction, then you count the number of true positive, then count the number of true false positive, and then you get the precisions, get the recall, and then you you sum up and everything together to get the final result. Compare it, plot it on the matrix table, you can see F1 score and PF1 score is kind of similar. Yep. So you can also play around with the beta information to see how like larger beta gonna have a higher PF1 score. So to sum up, I have shown you the 2 most common data-centric techniques to have your model generalize better in the test set. The first one is data augmentation, which is a process of creating new training sample from the existing one. This is quite easy to use and will help you introduce some variance to your data, which will have the model generalize better. But you need to be careful not to distort the image too much. The second one is evaluation matrix. Like by choosing the right matrix can help you penalize any false positive, which is a common factor in highly class imbalanced dataset. Yeah, so that's it for my part. If you have any question, can let me know.
Okay, perfect. Thank you so much. Let's take a chat. Let's take a look at the chat, see if there's any questions. Okay, seem. Yep.
Thank you.
So everyone's saying everything is very clear. So yeah, I'll merge the two videos and I'll upload them on YouTube. So yeah,
Thank you, Hossein.
no worries, no worries. Thank you guys for doing this, for making the nice notebooks. And yeah, tomorrow is going to be the last day, so it's a nice
Yeah.
ending.